Okay, so we will start proceeding with learning for week 5. So this is the doubt clearing session for week 5, where we will be considering the concept of inductances, like when they are coupling between two coils, two inductors, what happens, how to consider their effect in the circuit, and how to proceed with solving various networks. So we will look into that problem today, and we will be we will first go through some basic theory of understanding of how there are coupled inductors as well as mutual inductances of coils. They are calculated, how they affect how the voltages are induced from one coil by the current in the other coil, etc. All those we will consider those theory, and then after that we will be solving some demo practice problems we will be solving, and that will be the problems which are previous year assignment, and we will solve those things to try to get a basic understanding of how to proceed with circuits where there is mutual inductance. Okay. So this course, as we know, has been taught by Professor Tapas Kumar Bhattacharya of Electrical Engineering from IIT Kharagpur department, and so today we are trying to understand what is self and mutual inductance. So there are various things that you want to understand, like there is a dot convection, how the coils are constructed, how they are coupled to each other, etc. We will try to understand. We will also understand how the voltages are induced in the coupled coils, as well as how much energy is stored in the coupled coils. So all these things we will be exploring today. And once we explore that, we will be solving some circuit problems where there are coupled coils. Right? So one main thing which we want to do is the dot marking mutually coupled coils and its significance. Yes. So what do you mean by coupled coils? Let us consider just a simple network like this. This is a sort of voltage source. There is a resistor here. There is an inductor here, L1. There is another resistor here. There is another inductor here, L2. And there is a sort of mutual inductance between these two coils. So why does such a thing happen? Why does such mutual inductance happen is because, as we know, when current flows through an inductor, it will generate magnetic flux. So in case those inductors are close to each other, some flux which is generated, like the flux which is generated by this coil, by this L1, due to some current I1, will induce some voltage in this inductor L2, and that will be reflected actually. Similarly, when the current I2 flows to this inductor L2, it will also generate some voltage in the coil L1. So the effect of all this mutual inductance between coils, all those we have to take into account while doing circuit analysis. So this mutual inductance is like, it depends. It is equal. Like mutual inductance from coil 1 to coil 2 is same as the mutual inductance from coil 2 to coil 1. There's a proof also which we will be going through, as well as this mutual inductance depends on how we have constructed the inductors. It depends on the construction of the inductors. So that is an important thing to consider. Construction of the inductors, as well as how close, or let us say the proximity, how close the inductors are to each other, or we can say the proximity of the inductors. So how close they are to each other. So these things are there. So we will have to consider such factors when we are making the circuit. And these coupled coils and coupled inductors can have some specific applications. They have their own uses, which people use in various advanced electronic circuits as well. But that is beyond this level, this UD level course. So we will not be going into it. So now we will proceed further. So there's a dot marking on mutually coupled coils and its significance. So whenever there is a coupled coils, we have a dot marking. This marking is here as well as dot marking is here. So dot marking is placed on one of the terminals of the inductor. In one for inductor L2, it is placed at one terminal, and for inductor L1 also it is placed at another terminal. So this dot marking is there, and this dot marking is helps to know the polarity of voltages induced on both the coils. So the polarity of the voltage induced at one coil at the dot marking one coil, same polarity of voltage should be introduced at the dot marking of another coil. And to test or to determine the dot marking, there are various tests which are available, which are used to identify the dot polarity as well. Similarly, in the case of there's so this is these circuits are they are magnetically coupled as well as they are electrically connected to each other. But in case of, let us consider, the circuit of a transformer. This it is magnetically coupled. So this is a diagram of a transformer. Like there'll be some N1 turns over here, two turns over here. This will be the current I1 flowing in, current I2 flowing out. This will be the voltage V2 over here, as well as this will be a voltage V1 over here. So in the case of a transformer, they are magnetically coupled. The two coils are magnetically coupled, but they are electrically isolated. And there are many circuits in which many circuits in which this property of the transformer, that is, it is magnetically coupled, that this circuit as well as this circuit are magnetically coupled, as well as they are electrically isolated from each other. These two properties are exploited by various for various applications. They are exploited. Okay. So Deepak Kumar and Gokul, do you have any doubts or anything? Deepak Kumar? Okay. Okay. And what about Gokul? Are you able to hear? You're not yet connected to audio. Yeah. Okay. So today we'll be discussing about the mutual inductance as well as self-inductance of coils. How when the two inductors they are magnetically coupled to each other, how do we analyze such circuits as well as all that. Then I also consider the transformer. This is a circuit of a transformer where this is this is the primary coil, this is the secondary coil. Primary coil has N1 turns, secondary coil has N2 turns. This is the current I1 in the primary and current I2 in the secondary. So what we must remember for transformer, the two coils, they are magnetically coupled to each other, but they are electrically isolated from each other. So this property of transformer is used for various applications like various protection features, for various current sensing applications. This property of the transformer is found to be very useful. All right. So let's proceed. So there's a dot marking, which we will try to understand how the dot marking scheme is there and what is its significance, as well as the self-inductance. Okay, when how much is the flux linkage when the coil carries 1 ampere current? Okay, so the coil carries a current of I, then the voltage across it is L di by dt. And the terminal through which I is entering is a positive and the other terminal is negative. So what does it mean is, this is the symbol of an inductor. There's a current I flowing through it. Now we want to know what is the voltage across the inductor. We know the voltage across the inductor is given by L di by dt. but we don't know which is the positive terminal. This could be the positive terminal, this could be the negative terminal. That we don't know. And in our circuit, we need to know, we need to show which is the positive terminal, which is the negative terminal, what is the polarity of the voltage induced. So the polarity of the voltage induced will be given like this, plus minus. Because here current is flowing into the inductor. Okay, then the voltage will be L di by dt. Okay, so this is how we determine the polarity of the voltage induced across the inductor. Right? Now mutual inductance between two coupled coils. So the flux linkage with the second coil when 1 ampere flows to the first coil, or the flux linkage with the first coil when 1 ampere flows to the second coil. Right? So let us consider two coils. There is coil L1, this current I1. Okay. There's this inductor L2, coil L2, and current I2 which is flowing through it. Okay. Now, when current I1 flows through L1 and there's no current flowing through L2, okay, that means what it means is there's some current I1 is there, right? The current I2 is equal to 0, and because of these coils that they are magnetically coupled to each other by a magnetizing inductance M. So there will be so what happens if this current I1 flows through this inductor, through this coil, and current I2 is 0, then there will be a voltage which is induced in the second coil, and that is given by M into di1 upon dt. Okay, so that is the voltage which will be induced. Okay, and similarly, if there is a current I2, which will be flowing and current I1 is 0, then another voltage will be induced in this inductor L1, and that also will be given by M into di2 upon dt. Okay, that is a simple concept. So we can come to the M12 is equal to M21. Okay. Now, also we know that the energy stored in an inductor is given by half Li square. So the energy stored by this inductor is half L1 I1 square by this inductor is half L2 I2 square. But we must not forget that this energy is stored in the magnetic flux also, which is linking both the coils. And that energy stored is given by M into I1 into I2, and there's some derivation which proves this fact. So the total energy stored, which is stored is given by half into L1 I1 square plus half into L2 I2 square plus M into I1 into I2. Okay. So any doubts here, Deepak Kumar, Gokul?
No, sir.
So we will proceed further. And okay, as well as there's a condition that I1, I2 are the coil currents which are entering through the dot terminals of the coils. Okay, so that we'll have to consider. So let us consider what they have written over here. There's a stationary coil. Stationary coil means it is not moving. Like there are coils which are placed in the motors, etc. At that time, those coils are moving, and then the effect also is same. Like there's some EMF induced, and that's how the magnetic flux, magnetic fields they interact, and because of that interaction, there is the rotation of motors. All that is there. But now let us just consider stationary coil. Stationary coil means it is not moving, and this coil has n number of turns. So when we make an inductor, sometimes we have to make our own inductors because the value of inductance which we want for our application is not available. It's not a standard value and that is not available. So we have to make our own inductor. So what they do is they take a core, they take a bobbin, then they mount some wire across the core, and that so when they design it, they have to decide what will be the number of turns n. There's a procedure for designing for an inductor, for a transformer, etc. There's a procedure. But one of the main criteria while designing that is we want to determine how many number of turns will be required. So that is an important factor. So let us consider that there are n number of turns and their flux linkages. Okay. So the number of flux linkages is 5 to the n into 5. Okay. Now this flux 5 happens to be a function of time. So when this flux is a function of time, there will be a voltage induced in the coil, and that is given by E to the n into d phi by dt. Okay, now because n is constant, we can take it inside, and we can say that the EMF induced is just a directly proportional to the change of the flux linkages to the coil. Okay. Now, this total flux linkage to the coil may be due to its own current or due to a number of other current carrying coils having mutual coupling with the coil being considered. Now, we have, according to this derivation, it says that the EMF induced is equal to the change of the flux linkages with that particular coil. Now, that flux which is linking to the coil, it could be coming from the current flowing through the same coil, or that flux would be due to the current flowing through some other coils which are magnetically coupled to the first coil. Okay. Now we will consider dot convention. So the dot convention is a very important thing, and because it is really the dot convention is really required if you want to analyze these circuits where there are coupled inductors, coupled coils are there. Okay, so let us consider a simple transformer. So if we know there's a laminated iron core, this is the primary winding. So this is the primary winding where we apply a voltage, and this is the secondary winding. So the primary winding has n1 number of turns. So similarly, in a transformer also, we basically one main criteria is we have to decide the number of turns, what is the turns ratio, etc. So we'll consider that there are n1 turns in the primary and n2 turns in the secondary. Okay, so if the number of turns in the secondary is more than the number of turns in the primary, then it's a step-up transformer. If the number of turns in the secondary are less than the number of turns in the primary, then it is a step-down transformer. Okay, so now we will see that the coils are wound like this. Okay, so the current is flowing. We apply voltage over here, and the current flows like this and goes like this and keeps on going like this. So this is the direction of the flow of current. Okay. Now, when this is the direction of the flow of current, an EMF will be induced. It will generate flux. Okay, a flux will be generated, and that flux will mainly travel through this laminated iron core. So why does this flux mainly travel to the laminated iron core is because the permeability or the reluctance, that is the reluctance of the iron core is very less as compared to the reluctance of the air. Okay. So the most of the flux which is generated by the primary coil goes through the laminated iron core. There is also some other flux which gets leaked through the air, etc. That also is there, but most of the flux travels to the laminated iron core. So when this flux travels to the laminated iron core, okay. Now there will also be suppose there is a secondary winding which has n2 number of turns. Okay, and we connect a load over here. So now the current could either be flowing in the inward direction or it could be flowing in the outward direction. Okay, so we don't know in what direction the current will flow. But what we know is by Lenz's law, the EMF which should be induced in the secondary coil should be induced in such a manner that it will oppose the cause of that EMF. So the cause of the EMF is just now what's happening is this flux which is flowing in this, which is there in this core, it is time varying. It is varying with time, and because it is varying with time, an EMF E2 will be induced in the secondary of the transformer. So this EMF E2 should be induced. When this EMF E2 is induced and a load is connected, there will be current which will flow. Okay, a current will flow. So this EMF E2 must be induced in such a way that when the current flows, the magnetic flux which this current will generate must oppose the original phi t flux. Okay, so we want that the current I2, that there must be some sort of current. Okay, let us assume there would be some sort of current I2. Okay, we want this current I2 must flow in, it could either flow in this direction or in this direction. If it is flowing in this direction, it does become negative. So we want this current I2 to flow in such a way that it will oppose, that it will generate a flux. This current I2, when it flows to this coil, it will generate its own flux. So that flux which it generates should oppose this flux phi t. So what we want is that the flux which this coil generates should be in this direction. Should be in this direction. So that it will oppose this flux which is in this direction. Okay. That is what we want. We want this flux to oppose this flux. Okay. And for that, what we would require is that the current. So if we want the flux to be generated like this, by according to Lenz's right hand rule, okay, according to that Fleming's right hand rule, the flux which is generated, it depends on, like, see, like we have our, it's not visible. This is my right hand, okay. So my these four fingers, it's not properly visible, okay. So these four fingers denote the direction of the current. So the current is flowing in this direction, like this. If it is flowing, then the flux which is generated will go in the top. But in case the current was flowing like this, then the flux will go in the bottom direction. Now what we want is that the flux should go up. So for the flux to go up, the current should flow like this, right? So that's why. So that's why what happens is there will be a positive terminal 1 minute. So this would be positive, this would be negative. Okay, when this is positive, then a current will flow out like this. Okay, and that is what generates this flux which is in the upward direction. All right. So that is how, what we can say is the dot convention states that when this terminal is positive, this terminal also has to be positive. That's how we will identify which is the dot. All right. That is how it is experimentally that is how it has to be identified. And to do that, there are various tests such as this polarity test or a DC kick test. So such tests they give, and they use to determine the polarity and determine the dot convention, that is known as polarity test or DC kick test. So the what key takeaway for you guys from this explanation is that when there are circuits involving coupled coils are there, okay, there's a dot marking which is there. A dot marking has to be provided so that you can properly analyze. And if those dot marking is not available in some experiment which you are doing, you have to perform this polarity test or DC kick test to determine the dot polarity. Okay. So one thing to keep in mind once a dot polarity is given is that at any instant, polarities of the dot terminals will be alike. So if here the voltage is positive, here also the voltage has to be positive. So that you have to keep in mind. Okay. Now we will consider self-inductance and mutual inductance. So Gokul and Deepak Kumar, do you have any doubts now?
No, sir.
Okay, so that's good. So you can stop me anytime if you are having any problem or anything. Okay. So let us consider transformer having two coils. So basically, this is just a proof of how it just states that the mutual inductance from coil 1 to coil 2 as well as the mutual inductance from coil 2 to coil 1 is the same. Let me just draw it to verify the point. This inductor L1, there's a dot. This inductor L2, there's another dot. There's some current I1 which is flowing, some current I2 which is flowing, and there's some sort of coupling between the two. Okay. So the coupling from, let us consider coupling from inductor L1 to L2. That is M12 is the magnetic coupling from inductor L1 to inductor L2. Similarly, there's a magnetic coupling from L2 to L1. That is M21. So M12 is what? It is basically because of the current I1 which is flowing through the coil, first coil, it will, the flux that is generates, that will get linked with the coil L2, the second coil. Okay. That is given by M12. Similarly, when current I2 is flowing through this circuit, through the second coil, it will generate some magnetic flux which links with the coil 1, and that is given by M21. All right. So that's what. So what the derivation states that this M12 is actually equal to M21. So that is, this is a standard thing which you must remember, and there's no need to go through the derivation and understand. In the, while solving the problems, we just have to use this fundamental thing that the mutual inductance from one coil to the other coil is fixed. Okay. Okay. Hmm. Now, now we want to know the polarities of the voltages induced in the coupled coils. So we first we studied that the polarity of the voltage should be same at the dot terminal. Okay, when the coils are coupled to each other. So now the voltage which is induced in any particular coil. So this voltage which is induced across a coil is a function of the self-inductance, the current flowing through the that inductor. This is a function of the mutual inductance, as well as the current flowing through the other inductor. Okay, to the coupled inductor, current through the coupled inductor. So it is a function of this. That's why the voltage is not directly just dependent on the self-inductance and the current flowing through the inductor. So let there be two coils with self-inductance L1, L2 and mutual inductance M between them. Also, we will consider currents in the two coils be I1 and I2. Huh? So voltage drop across coil 1 will be sum of two drops, namely L1 di1 dt and M di2 dt. Okay. So for this coil L1, the drop, some sort of drop. Okay. The drop across the across this inductor L1 is L1 di1 dt. That is one part of it. Another part is M into di2 upon dt. Now we do not know whether this is positive or negative. This depends on the direction of current. This depends on the polarity, depends on the dot convention, etc. So this, so main goal of this section which we are studying right now is to understand how will we determine what will be the polarity of the voltage. Okay, that we will consider. So that we said the voltage across one coil is drop of this L1 di1 dt and M into di2 by dt. Similarly for the other coil, it is L2 di2 dt and M into di1 dt. So we know, to know which is the positive and negative sign for voltage drop due to self-inductance. So we know over here, for here, this will be positive, this will be negative. Okay, just consider, I'll make a better diagram. L2 dot mutual inductance M. Okay, this current I1, this current I2. Assume it like this. So the voltage across L1, VL1T is equal to L1 di1 dt plus or minus M into di2 for dt. Okay, this is the voltage drop. Similarly, voltage across inductor L2 VL2 T will be L2 into the current flowing through that same inductance L2 di2 upon dt plus or minus, we don't need polarity, we have to determine that, M into di1 upon dt. Okay, so now the main goal is to find which is positive, which is negative, as well as for this drop. This drop always we are taking it to be positive. The drop due to self-inductance is always positive, and that is in the direction of the flow of current. Okay, so in this case, the current is flowing out of the circuit for the coil 2. So over here, this will be where it will be positive, and this will be where it is negative. But in this case, current is flowing in. So at what point the current is flowing into the circuit, there will be the positive polarity of the self-inductance, and where it is going out of the coil, it will be the negative polarity of the self-inductance. All right. So that's what they have told here. So first thing is voltage drop due to self-inductance L. Whenever a coil carries a current I, there is a voltage drop L di upon dt, and the terminal through which the current I is entering is the positive terminal, and the other terminal is negative. So that's what I've just told over here. Similarly, voltage drop in coil 2 due to mutual inductance M. So if this I1 is entering to the terminal, to the dot terminal. So let's see over here. I1 is entering to the dot terminal of this coil L1, of this coil. Okay. Then voltage, the voltage is induced due to mutual effect in the second coil, M into di1 upon dt, will have positive sign on the dot terminal of the coil 2. So because there is a current I1 flowing over here, and it is entering the dot terminal, there will be a voltage which is induced in the secondary side, which will have a polarity, positive polarity. So it will have positive polarity over here and a negative polarity over here, and it is given by M into di1 on dt. Okay, that is the mutual inductance. That is the voltage induced due to mutual inductance or coupling between the two coils. Okay. Okay. And so now the voltage, let us, so this voltage over here, okay, BL2, it consists of two things. As we said, it is consists of the drop due to this inductance, as well as due to some magnetizing drop due to the magnetizing to the coupling inductance, the magnetizing inductance. So let me further simplify this. This will be written like this. Okay, this is current I2 which is flowing out, and here one more polarity like this. This will be VL2 plus or minus. Oh, this will be minus, this will be plus, because the current I2 is flowing like this. It is entering over here and just leaving over here. So this will be the component due to self-inductance. L2 di2 upon dt. All right. Now for the coil M1, the coil 1, current is entering over here. Current is entering the dot terminal. So at the dot terminal, which is over here, it should have a positive polarity. Okay, it should have a positive polarity. So it will be plus minus m into di1 upon dt. So when we consider this polarity and we apply KVL, what we get is VL2 upon T is equal to L2 di2 upon dt is a function of time minus m into di1 upon dt as a function of time. Any doubts to this? This is very important.
No, sir.
No doubt.
No, sir.
Okay. What about Deepak Kumar? Hmm? Okay. Now we will try to find the voltage across the inductor L1. Okay. That is, now here current is flowing inwards. Right. So it will be given like this. I1 plus minus L1 di1 upon dt. Okay. Then now we want to know what will be the polarity of the voltage which is induced due to the magnetizing inductance. That is what we want. So one criteria is this the dot. At the dot terminal, what we will do is we will just directly put a positive at that end and a negative at that end. Okay. Then we will directly write m into d of dt. Now we want to know what is the direction of current. Over here, current is flowing out. That is I2 is negative. It is not entering. It is flowing out. So what we write over here is m into d of minus I2 upon dt. So effectively what do we get is this VL1. Okay. This VL1 of t is equal to L1 di1 of dt minus m into di2 of dt. Okay. Any doubt in this?
No, sir.
Hmm. So this is all we need to remember while while solving these couple inductors based couple coils based circuits. Yeah. So they have also given us, they have used some other method. It's a bit complicated according to me. So, but just let us just go through what they're saying. There's an inductor L. There's a current I which is flowing. Okay. Remember, this current I is a function of time. That is, it is varying with time. It's just a function of time. It could be either constant or varying with time. But in case the current was just a constant value, then the voltage across the inductor would be zero. Okay. Suppose the derivative of constant is zero. So this is the positive terminal, this is the negative terminal because current is flowing inwards like this. So that will be positive. So we represent it as L into di upon dt. And positive terminal is where the current is flowing in and negative terminal is where the current is flowing out. Similarly over here. Okay, now current is flowing in from here. That's why, so that will be the positive terminal. So this will be the positive terminal, this will be the negative terminal. So this will be L di by dt. Okay. Now we will consider two coils are here. Two coils are there. They're magnetically coupled by some magnetizing inductance M. By this mutual inductance M. Okay. So this is I1T, this is L1, this is I2T, L2. So because current is flowing in from here, that's why this will have self-inductance will be L1 di1 dt with positive at near the dot. Okay, and negative over here. Now for the mutual inductance, it will be M into d of dt. And now we have to write the polarity of the current over here. Okay, so positive will be at the dot part, the negative will be at the other terminal. All right, m into d of dt is fixed. Now, depending on the direction of I2, if I2 here I2 is flowing in, that's why I2 is positive. So that's why the effective drop is L1 di1 dt plus m into di2 of dt. Similarly, that will be the case for the other coil, for the other coil over here. But we will consider this case, where current is flowing into the dot over here and current is flowing out of the dot over here. Here, what is actually happening is current is flowing out to the dot like this, I2. Okay, the current is flowing out to the dot like this. So, what is happening is for this, let us consider for this one. Current is flowing in over here. So it will be positive, negative, L1 di1 dt. This is for the self-inductance. For the magnetizing inductance also, at the dot terminal, we just consider to be positive. At the other terminal, we consider to be negative. Positive, negative, M into d of dt into the current. Now, over here, the polarity of the current is negative because it is flowing out. So this will be minus of I2. That's why the effective voltage drop will be L1 di1 dt minus M into di2 upon dt. Alright. So if we take the rubber and rub this off, that's the same thing which we get over here. Same thing. Okay. So this is the way it will help us to solve the circuits fast and to complete it on time. Alright. This is the easier method than rather using a square symbol plus a dot symbol, etc. That I feel is a bit time consuming, but in case you find it useful, you could use it. There's no one stopping you. All right. Okay. So there's a derivation over here about the energy stored in mutual coils. So voltage drop in coil 1. So the voltage drop in coil 1, they found it to be L1 di1 dt plus M into di2 upon dt. This has been found because current is flowing into the terminal for this inductor, for this coil, as well as it is flowing into this coil as well. Therefore, there's positive polarity. So there's L1 di1 dt plus M into di2 by dt. Similarly, voltage drop in coil 2 is given by this L2 di2 dt plus M into di1 dt. Now, the power absorbed by the coils is just the voltage drop into the current. Alright. Now, the energy supplied to the coil in time dt is dw equal to power into dt. So, this is the work done, dw. Incremental work done for an incremental period of time dt. Alright. We write it in this form. So, what they do, this dt and dt get cancelled. So it comes out to be L1 di1 I1 plus M into di2 I1 plus L2 di2 I2 plus M into di1 I2. So they write it as L1 I1 into di1 plus L2 di2 di2 plus M into di2 I1 plus di1 into I2. That you can write it in the compact form as M into derivative of I1 into I2. So when there's a product term and we take the derivative, it comes in this format. So we have just gone in the opposite direction. Alright. So this is the incremental work. Now we want to get the work, the total work done. So that is the total energy stored when we go from 0 to time t. Okay, so it will be L1 into integration 0 to I1, I1 into di1 plus L2 integration of 0 to I2, I2 to di2. Okay, we get these values and then we integrate, we get it in this form. All right. Work done is half L1 I1 square plus half L2 I2 square plus M into I1 into I. So any doubts in this concept?
No, sir.
Now, many times what, okay, I'll just ask you as a simple doubt. Uh, okay, this is a circuit over here. There's two coils L1, L2. There's a with the mutual inductance M. right? This is the input voltage. This is the current I1. This is the current I2. All right. So now we want to know what is the effective impedance seen by this voltage source. So how will you determine that? Any idea? Deepak Kumar, can you tell? What about Gokul? Gokul, how do you find the input impedance for anything?
Sir, V in divided by I in, sir. Input impedance.
So what is the I in over here? So which is the I in over here? Hmm. So as the equivalent impedance, so can you see my screen, right?
Yes, sir. Yes, sir.
Yeah. So many times we want to know what is the equivalent inductance or the equivalent impedance seen by the voltage source. Okay, seen at this point. Okay, what is the equivalent impedance seen at this point? A and B. Okay, that is one of the goals or targets. What do we do that? That is simple. We just what is the voltage applied? What is the current flowing? The equivalent impedance Zn is equal to V in upon I1. Okay, that is the input current. So if we can find that value, that will actually be the equivalent impedance, equivalent input impedance. Okay. So there are some questions where we have to do that. We have to find the equivalent inductance seen between the two terminals. So we use that same method. We apply some voltage, we see what is the current flowing, and we take their ratio and we find the equivalent inductance. All right. So the screen is visible, right? So we'll proceed further. Now, let us consider the case when the coils are shorted. Okay. Um, so they have self-inductance L1 and L2. There's a mutual inductance M over here. Okay. And we have shorted the second coil. So now we will try to derive this. What we have done over here is basically we have just connected this in short circuit like this. Right? Okay, here the dot polarity also is different. One minute. Okay. Direction of current also is different. Right? So what happens is this V2T is 0 because it is shorted. V2T is equal to 0. And because and the voltage across it will be L2 di2 of dt plus M into di1 of dt is equal to 0. Alright, this will be the voltage over here. Similarly, for voltage over here, when we apply KVL for the first coil, we get it be Vn is equal to L1 into di1 of dt plus m into di2 of dt. Alright. So when we simplify this, what do we get is di2 of dt is equal to minus m upon L2 into di1 of dt. So we get it to be of this form. Vn is equal to L1 di1 of dt plus m into d of di2 of dt we found out from here will be equal to minus m of L2 into di1 of dt. So that will be equal to di1 of dt into L1 minus m square upon L2. Alright. So in this manner, now you may ask, like, what is the actual equivalent inductance which is seen is? So equivalent inductance will be V is equal to L equivalent into di1 of dt. So when we compare, L equivalent will just be equal to L1 minus m square upon L2. Okay. So that's how we find the equivalent inductance, and that is what is shown over here. L1 minus m square upon L2. Alright. So any doubts in this thing? Gohil?
No, sir.
Alright. You're from Chennai, right? Your college?
Panimalar Engineering College. Panimalar Engineering College, Chennai.
Okay. Where is it actually?
Sir, Tamil Nadu, sir.
No. In Chennai, where?
Tamil Nadu, Chennai, sir.
Chennai, which location?
You know Pundamalli,
No.
Tambaram.
Tambaram.
Yes, nearby Tambaram.
But I'm also from Tamil Nadu, only, so I don't know Tamil. That's a problem. So let's go for this complicated circuit we will do, and based on like similar complicated circuits you will get in your assignments and all that stuff. So let us look at this circuit. Right. Look over here. Page 1 minute. So this is the circuit over here. All right. Now there are 3 inductors, and there are various mutual inductances also over there. Now we want to write the equations of the voltages which would be induced, everything. All right. So what we will do is we will draw the effective circuit. This voltage source will remain fixed. Okay, V1. This is a resistor R1. Now, because the current is entering into the inductor L1, this will be plus minus L1 di1 of dt. All right. Now, for magnetic flux, due to mutual inductance M3, the current is entering in through I2. That's why it will be given as at the dot it is entering in, so it will be plus minus, because the dot is over here, this is the plus terminal, minus M3 into di2 of dt. Okay. Similarly, for the mutual inductance between these two coils, it will be plus minus M1 into d of dt. Now the current we want to know. Here the current is flowing out of it. So that's why it will be minus of I1 minus I2. So it will be minus I2. No, it will be plus I2 minus I1. Okay. Because this is I1 minus I2 which is flowing out. So that will be I2 minus I1 which is flowing in. Alright. So this is how we get the polarity over here. Similarly, so any doubts for this part? How this has been found?
Sir,
Yes.
how I2 minus I1, sir? I cannot
Ah,
understand, sir.
yeah,
Please say, please say, sir.
This is the main. Yeah. For M3, it is simple. Okay. For any mutual inductance, at the dot, we consider positive. Alright. This is a dot side. Okay. So this positive. Does this make sense? See, there's this inductor. It has two terminals. One is a dot terminal. One is the not dot terminal. So for any mutual inductance, the terminal which is closer to the dot, that will be the positive. Terminal which is away from the dot, that will be the negative. Right? So that we have done over here as well as over here. Okay. Then we write whatever is the mutual inductance which is there. So this will be M1. Okay. M1 is the mutual inductance between these two coils into d of dt. This also will remain same. D of dt also will remain same. Into now the current. Now we want this will the current which should be written over here should actually be the current which is flowing into the dot. It should actually be the current which is flowing into the dot. Over here it is given that the current flowing out of the dot is I1 minus I2. That means the current which is flowing into the dot is just the opposite. That is the current flowing into the dot is I2 minus I1. So that we will write over here. That will be I2 minus I1. So did you understand this?
Sir, suppose same direction means what, sir? Same direction current means what? Sir?
Ah, see over here it is in the same direction because here current. Now you must, when we want to find a mutual inductance over here, due to the current flowing in this I2, we must only consider the direction of current I2. We must only consider direction of current I2. Okay, that's the main thing. We'll consider direction of current I2, which is flowing into the dot. Because it is flowing into the dot, we just put M3 into di2 of dt. We don't add any polarity sign over here. Okay. Similarly, for this coil coupled to this coil, we just do M1 into d of dt into the current which is flowing into the coil. Current which is flowing into the coil at the dot. And that current which is flowing into the coil at the dot is equal to I2 minus I1. Because I1 minus I2 is flowing out, you just multiply it by minus 1, that is I2 minus I1, that is the current flowing into the dot. Alright?
Okay, sir. Okay.
Now, I won't do for this one first. I'll just do for this one because we don't have much time. So, over here, there is this L2. Okay? Here, if we observe, so let us do for the mutual inductance. Okay? We will, this is the dot terminal. So, this will be the other terminal. Because the dot terminal is below, this will be positive, this will be negative. Okay? So, this will be M1 into d of dt into the current which is flowing into the dot, that is I1. Okay, so that we will just write it like this. Simple. Any doubt in this?
No, sir.
Similarly, for this inductance with M2, it will be minus plus M2 d of dt into the current flowing into the dot. Current flowing into the dot is I2. So we directly write it as I2. All right. Now, for the self-inductance, we know at what terminal the current is flowing into the circuit, that is the positive terminal. And what current is flowing out of the coil, that is the negative terminal. So it is flowing in from the top. So that's why the top will be plus, bottom will be minus. It will be L2 d of dt into I1 minus I2. This for this self-inductance. So is this clear? Hmm? Or should I repeat it?
Okay, sir. Repeat, sir.
Hmm?
Repeat, sir.
Okay.
Repeat again, sir.
Yeah. So this is the dot terminal, okay? Dot terminal is at the bottom. So when we find mutual inductance, bottom is a dot terminal, so bottom one will be plus. This will be plus, the other side will be minus. So that's the first thing. Then this is the mutual inductance M1. So we just write M1 into d of dt. Now the current which should be over here should be the current which is flowing into the coil, and that is I1. So we just directly write I1. All right. So that will be this voltage drop. Similarly, there's another mutual inductance M2. So because the dot is at the bottom, so that's why this bottom will have plus, this will have minus. This will be M2 into d of dt into the current which is flowing into this coil. Into it, the current which is flowing is I2. So we directly put d into I2 upon dt. Okay.
Okay, sir.
Then we have this. Now we want to find the drop due to self-inductance. So for self-inductance, we have to consider the direction in which current is entering this coil. So it is entering the coil from here. So here it should be positive, here it should be negative for the self-inductance. So over here we put positive, here we put negative. L2, which is the value, into d of dt into the current flowing in. Okay, that will be I1 minus I2. Is this clear?
Okay, sir.
Okay. So now we will start solving some problems. Actually, we will do this. Okay. So okay, there's this question. Okay. So now this concept of cup, the mutual inductance will be very important. So that we have to consider over here. So this is the question. Okay, so what we do is we will redraw this circuit. The actual circuit we will draw. Okay. So that will be there's this 100 volt RMS. And one more thing I forgot to say is wherever this d of dt is there, wherever this d of dt is given, we replace it by j omega. This is for steady state. Okay, last week we studied the concept of phasor analysis we studied. Okay, we studied the concept of phasor analysis. That is at one particular frequency omega, which is the frequency of interest, where the phasor rotating in the counterclockwise direction with frequency omega. So in that case, we can apply phasor analysis and we directly replace d of dt by j omega. So that is what we will be doing over here. That they have already done. They have given J36. The 36 actually is the L1. It is omega L1. 36 actually is omega L1. They've just directly given the value. They've not given L1 directly. Okay, so this is a sinusoidal voltage source of which has 100 volt is the RMS value. And in our question also, they asked you to find the RMS value of I1, I2, etc. So that's why we can just directly use the RMS value. Right? So this is the 100 volt input voltage source. Then we have this 36J. This is the self-inductance. Now, these are the where we get the this is the dot terminal. Dot terminal is at the top of the inductor. So we put plus over here, minus over here. Then the coupling inductance, the mutual inductance is given by J into 8.4. Okay. So for this one, the current is flowing. So for here, at this dot, current is flowing out of the dot. That's why this will be equal to J into 8.4 into minus I2. Okay. So this will be the drop across this voltage source, across the voltage which will be induced in this coil due to current I2 flowing through this coil of J4 self-inductance. This drop will be J into 8.4 into minus I2. Alright. Plus is because at the dot we put the plus. J into 8.4 is the mutual inductance part. Minus I2 is the current which is flowing into the dot. Into the dot. Okay, so we write it like this. Similarly, this coil is also coupled to this coil by same J 8.4. That also we write it as like this. Plus at the top, minus down. J 8.4 is the same. Now here I2 is flowing into the dot. Okay, here I2 is flowing into the dot. So this will be I into 2. Okay, and this directly completes the circuit. Any doubts in this part, Gokul?
No, sir. No, sir.
Okay. Now for the other terminal. Okay, now the other terminal is there. That also you must consider. So we have this J4 is for the J4 is because of this self-inductance to this coil. This coil is coupled to this coil as well by J 8.4. And this is the dot. Dot is at the top. So that's why this will be plus minus J 8.4. Now the current flowing into the dot is I1. So this will be directly I1. Another thing is this is coupled to this coil also. This is coupled to this coil with J 11.2. So that's why we just put here plus because of the top is a dot. So we put plus on top minus J 11.2. Here I2 is flowing into the dot. So we directly put J 11.2 into I2. Okay. This is point A. This is point B. Alright. This is the 40 ohm resistor over here. Similarly, now this coil is coupled to this coil by J 8.4. Okay. So it will, and the dot, you must keep in mind, dot over here is at bottom. So this will be, dot is at the bottom. So plus will be at the bottom. Then J 8.4. Now I1 is flowing into the dot. So that's directly J 8.4 into I1. Alright. Similarly, this coil is coupled to this coil also by J 11.2. So we write it, and dot is at the bottom. So it will be minus plus J 11.2 into, now depends on the current. Here the current is flowing out of this.
Sir,
Yes, yes, yes.
J 8.4 minus I1. Now, why, sir? Plus I1, you write, sir. It is minus I1 only comes, sir. Because I1 is entering, this I2 is leaving. So minus.
Where it will be means?
Sir, in second circuit, sir. Plus J 8.4 into I1, you write, sir. But actually minus I1 3 comes, sir.
Here.
Above, sir. Above.
Over
Yes,
here.
sir. Yes, sir. Yes. Yes, sir. Yes, sir.
Okay. Over here, right? No, here it will be I1
Yes, sir.
only.
Yes, sir.
It will be
How,
I1
sir?
because I1 is entering the dot, right?
Yes, sir. Yes, sir. I1 is entering, sir.
Hmm. So it will be that. Okay.
Okay, sir.
Hmm. Then this will be J into 11.2 into I2. Then we have the drop due to the self-inductance, that is J into 49, and this completes the circuit ABC. Okay. So the current I2 is flowing like this. Current I1 is flowing like this. Alright. So now when we will apply KVL over here, what we will get is this voltage source and this voltage source, they cancel out each other. Because this is minus J8.4 I2, this is plus J8.4 I2. So the effective KVL is 100 minus 36J into I1 is equal to 0. That's why I1 is equal to 100 upon 36J. So can you calculate and tell how much is that? Hmm? 100 upon 36, how much is it?
Okay, sir. Okay, sir. Wait, sir. Wait, sir. Minus 2.77 J, sir.
Why will be minus? Oh, okay. Consider J. Don't consider J because
J terms. Yes, sir.
J is just J is for the phasor quantity. Okay. So they have told in the question to find the RMS value. Okay, you want to find the RMS value. So you can neglect J in that case. Because RMS value means we just want to find the magnitude of this, right? And magnitude of J is actually equal to 1. So we can ignore J. Okay. Any doubt in that?
No, sir. No.
Similarly, when we apply KVL in this loop, okay. One more thing I forgot to say. Here it will be plus is down because this is down, minus over here J 11.2, and here I2 is leaving out. So this actually will be minus I2. J 11.2 into minus of I2. Okay. When we apply KVL over here, what we will get is, so this is, how can I write some mistakes? This is I2. Okay. So it will be minus J4 into I2 minus 40 into I2 minus J49 into I2 minus this goes like this. So minus minus becomes plus. So it will be plus 11.2 J into I2, and this also becomes, and this voltage source and this voltage source cancel out because they are of opposite polarity. Then another plus 11.2 J into I2 is equal to 0. Now it is all I2 in terms of some value. Okay, and because it is like that, that means I2 is actually equal to 0. Okay. Hmm?
Okay, sir. Okay, sir.
So we got I2 to be equal to 0. So we have solved I1, I2 we have got. Now they were telling us find the RMS value of the potential difference between A and B. So we want to find the potential difference between A and B. Okay. Between A and B, what we know is I2 is equal to 0. Okay. I2 is equal to 0 means J4 into I2 is 0. Oh, I'll just write it down because it should not be confusing. So we want to find the voltage between A and B. So VAB minus, we are going like this. So plus becomes plus 11.2 JI2 plus 8.4 JI1. And because it's an impedance, it is minus J4I2 is equal to 0. Now I2 0, I2 0, so these two terms become 0. So VAB is actually equal to minus 8.4 JI1. What is I1, which you calculated?
2.77.
You multiply that by 8.4, how much you get? Secret, fast, fast. How much you get? Hmm?
Wait, sir.
So
Wait, sir. Minus 23.268. Yes, sir.
yeah, it will be minus 23.268. Okay.
268.
That is fine. Okay. So now we just have to consider RMS values. We just take the absolute values, that is 23.2 something. Okay. So that is how we get the value, which is correct from 23.2. Okay. So now we will proceed to the next question. Are you able to see my screen now?
Yes, sir. Yes, sir.
Are you able to see, right? The screen.
Yes, sir. Yes, sir.
So now we will consider this sum. All right. So again, we will construct the equivalent circuit like how we constructed for the last example. Okay. So it comes out to be like this. This is the 100-volt thing over here. Okay. J16 as previously I1. Then this is the voltage which is induced due to the coupling. Okay. First directly, where's the dot? We put positive over there, minus over here, close it. J into 9.6 is the mutual coupling. Now into the current. we want the current that is flowing into the dot. And the current that is flowing into the dot is minus I2. So this will be J into 9.6 into minus of I2. Okay, so this is one thing. Similarly, for the next part, it is J into 36. Then the coupling from magnet mutual coupling. Okay, so at the dot, this is the dot part, so this will be plus. This will be minus J into 9.6 into the current flowing into the dot over here. Current flowing into the dot is I1. So this will be J into 9.6 into I1. Similarly, there's this J49 because of this one. Then add this a dot. This is the top part. So that's why over here the top will be plus, this is minus. J into 8.4 into the current flowing into this dot. That is minus I3. That will be minus of I3. Okay. So this is the middle circuit. Similarly, for the final thing, it is J4. Then dot is over here. So positive will come there. Positive, negative. J into 8.4 into the current that is flowing into the dot, that is I2. So it's over here I2. Here it will be minus 15J. This is I3. This is I2. This is I1. Any doubt in this?
No, sir.
Sure. Hmm?
Yes, sir. No doubt, sir.
Okay. So now we will start solving. What we will do is we'll apply KVL for the first circuit. Okay. We apply KVL in loop 1. Okay. So that will be 100 minus J16 I1 plus minus minus and one more minus will become plus. So plus J 9.6 I2 is equal to 0. Okay. So we write it down as 100 is equal to J16 I1 minus J 9.6 I2. So this is equation A. Okay. Then we apply KVL in loop 2. Okay. When we apply KVL in loop 2, we get minus J36 I2 minus J 9.6 I1 minus J49 I2 minus J 8.4 into minus I3, so plus. So this will be plus J 8.4 I3 is equal to 0. So we get it to be minus J 9.6 I1 minus J 85 into I2 plus J 8.4 into I3 is equal to 0. This is B for KVL in loop 2. Okay. Now we apply KVL in loop 3 over here. We apply KVL in loop 3. What do we get is minus J4I3 minus J8.4 I2 plus 15J into I3 equal to 0. Okay. So we get 11J I3 is equal to 8.4 J I2. Any doubts in this?
No, sir. No.
Hmm. Okay. So we get I3 to be equal to 8.4 upon 11 into I2. Is this clear? Hmm? Okay. So now we got I3 in terms of I2. Okay. Now we substitute this I3 in this equation. Okay. So we will get it be of this form. No, actually, I made a mistake. So what we must understand here is the inductance, right? At this dot. So at this dot is the positive terminal. This dot is the negative terminal. This is correct, actually. But this one at this dot, J 9.6 into I1. So dot is at this side. So this should be the positive thing. So actually there was a mistake in the polarities. So so Gokul, actually for this one, the dot is over here. Dot will be at this part. Okay. So this will be the positive thing and this will be the negative thing. Similarly, over here for this inductor, the dot is at this part. So the dot will be over here, plus over here and minus over here. So this mistake I had made, this mistake I'm correcting. Okay. So if we consider like that, then this will actually be a plus over here. When this is a plus, this will come to be minus 8.4 upon 11 I2. So I3 is equal to minus 8.4 upon 11 into I2. So similarly in this KVL also, this will actually be a plus J into 9.6 into I1. Okay. So that we must consider. Okay. So now let us proceed. Are you able to see my screen everything, right? Google?
Yes, sir. Yes, sir.
So now in B we substitute value of I2. I2 will find to be minus 8.4 and minus 8.4 upon 11. No, I3 is minus 8.4 upon 11 into I2. So that's why J into 9.6 I1 minus J into 85 I2 plus j into 8.4 and I3 is equal to minus 8.4 upon 11 into I2. This is equal to 0. So that will be equal to 9.6 j into I1 will be equal to minus j into I2. So can we solve it? How much it comes? 85 into, this will be 85 plus 8.4 into 8.4 upon 11. 8.4 into 8.4 divided by 11. That will be 6.4145. This is equal to 0. So on simplifying, we get 96 I1 is equal to 85 plus 6.4145 I2. That is equal to 91. No, sorry. This is 90 J 9.6. Okay. This is 9.6. Dot is over here. So this is 9.6 I1 is equal to I2 into 85 plus 6.1415. That is I2 into 91.4145. That's why I1 is equal to 9.5223 into I2. Okay. This is what we get. Now when we substitute this value of I1 into A, okay, so we get 100 equal to J into 16 into I1, that is 9.5223 I2 minus J into 9.6 into I2. That is equal to J into I2, 16 into 9.5223, 16 into 9.5223. Then we subtract from it minus 9.6. So we get it to be J into I2 into 142.7568. Okay. So when we divide 100 by 142.7568, we get the value of I2 to be equal to 0.7005 ampere. Okay. This is the value of I2. I2 we get it to be 0.7005 ampere. So this is the RMS value of I2. Similarly, when we put I1, I2 we put 0.7005 into this expression, we get it to be 0.7005 into 9.5223. We get it to be 6.67. This will be equal to 6.6705 ampere. Similarly, I3 is equal to minus 8.4 upon 11 into I2. We neglect the minus sign because in RMS we are not worried about that. So what's the value of I2 is 0.7005 into 8.4 divided by 11. That comes out to be, so that's why we get I3 be equal to 0.5349 ampere. All right. Any doubts in this?
No, sir.
Yeah. But for the direction purpose, this is the magnitude of RMS value, but for the direction purpose, this will be minus. All right. So now we want to find the voltage V2. We are asked to find the voltage V2. So V2 is basically from here. This is the voltage V2. All right. So voltage V2 is the drop across this J49 ohm inductance with I2 plus this one, this drop over here. That's why we get V2, there's no space actually. So we get V2 to be given by V2 minus J49 I2. Okay, V2 minus J49 I2. And this will be minus J8.5 to minus I3. So it becomes plus. So that will be V2 minus J49 I2 plus J 8.4 into I3 is equal to 0. So V2 is equal to J into 49 I2 minus 8.4 into I3. Okay. So we know the value of I3 to be equal to minus 0.5349 into minus 8.4. Okay. Plus 49 into I2, that is 0.7005. That's why we get V2. Once we do the calculations, we get V2 to be equal to 38.8176 J. We neglect J. So the RMS value of V2 is 38.8176 volt. Right? Then we have to find the voltage V3. V3 is just I3 into minus J15. Okay? V3 is I3 into minus J15. So V3 minus I3 into minus of J15. Okay? So this is equal to V3 plus J15 into I3 is equal to 0. So we get V3 is equal to minus J15 I3, which is equal to minus J into 15 into I3. The value is given by minus 0.5349. Okay, minus 0.5349. That will be 15 into 0.5349. So that will come out to be 8.0235. That is equal to J 8.0235 volt. Alright. So we have found the RMS value of V2, we have found the RMS value of V3. And we have found the value of I1, I2, and I3. Alright. So Gokul, any doubt in this?
No, sir.
Now we will do the sum, the final sum. So there's inductance of J9, inductance of J4, and the mutual inductance is J3. Alright. So we want to find the coefficient of coupling. So do you know what's the formula for the coefficient of coupling?
Sir, MC equal to K into root of L1 into E2, sir.
That is going to K equal to M1 square root of L1 into L2. So what is the value? Can you calculate and tell me? Is it taking so long? This M is just equal to 3. Sorry?
Wait, sir. Calculating, sir. Wait, sir.
Sure.
Point 5, sir.
Yeah, correct. Okay, so try to increase your speed. Yes, this is the coefficient of coupling. Next, we will draw the equivalent circuit as we always do. So this will be equal to this 80-volt voltage source will remain the same. This is this J9 over here, and this will be the dot. We give the positive. That is at the top. We give the positive, negative down. J into 3. Now here I2 is flowing out. So that's why this will be minus. This will be minus I2. Okay, so this completes this first circuit, I1. Similarly, for the other one, it is actually J4 dot over here, and over here it will be equal to minus and plus. Positive over here, so plus over here. J into 3, and I1 is flowing in, so I1. So this will complete the circuit. So when we apply KVL in the second loop, we get this is equal to I2. Okay, so it will be minus J4 into I2 plus J3 into I1. This is equal to 0. So what do we get? 4I2 is equal to 3 into I1. Okay, so I2 is equal to 3 by 4 into I1. Alright. Similarly, when we apply KVL in the first loop, we get 8T minus J9 into I1, and this minus, and this again minus, so it becomes plus. So it becomes plus J3 into I2 is equal to 0. So 8T equal to 9JI1 minus 3JI2. So that will be equal to 9JI1 minus 3 into 3 by 4 JI1. So that would mean 80 is equal to J into I1 into 9 minus 9 upon 4. So can you calculate and tell me what will be I1? Are you calculating?
Yes, sir. Yes, sir.
Yeah.
$11.85.
Okay. That's why I1 will be equal to 11.851 ampere. Alright. Now I2. I2 is 3 by 4 into I1. So how much that will be?
8.88, sir.
Yeah, 8.88. So Aman, Lovan, and she actually our session is almost ending. Just 10 minutes are remaining. Uh, so did you join late or what was the problem?
Sir, yes, sir.
No, there's some Aman, Lovan, she who has joined. So I'm asking you.
Okay.
Is it audible? Aman, Lovan, she, are you able to hear?
Yes, sir.
Okay, okay. I will proceed. We'll proceed. So we have found the value of I1. We have found the value of I2. Then next they've asked the question is we have to find the input impedance of this circuit. Okay, we want to find the input impedance of this circuit. So what will be the input impedance? Can you tell me, Gokul? Now, what's the formula? Go to you. Tell me the formula.
Sorry, sir, I forgot, sir.
Okay. So what this input impedance means is you want to find the input impedance of the voltage source. That is, this is the impedance. What will be the impedance across these two terminals? The voltage is this much, the current is this much. So we divide voltage by current, we'll get the input impedance. Okay. Is that clear?
Okay, sir. Okay, sir.
So that input impedance is 80 upon I1. What is the value of I1? Hmm? Local, I didn't hear. What's the value of I1?
Sir, can you scroll down, sir? 11.85, sir.
Okay, so 80 divided by 11.85 is how much?
Sir, 6.73, sir.
Yeah, yeah. Okay, so it becomes 3 equal to 6.75. Okay. So, congratulations, we have successfully completed solving the assignment. All right. So one thing I'd like you to keep in mind is they were told you to find the RMS value. So that means you don't have to put the sign. Okay, in the answer, if you put the negative sign minus something, then you will get the answer to be wrong. So if they say RMS value, just be the magnitude. Okay, so that you must
Okay,
know.
sir.
Yeah. Then it is written in ampere. So in ampere means it will be in ampere. If they put in milliampere, means you have to multiply it by 1,000. So what dimensions? No, dimension will be same, will be ampere only. But what units, like which is in milliampere, microampere, kiloampere, something like that. Similarly for ohm, it could be kilo ohm, it could be milliohm. Such things you must be watchful and you must be careful. RMS value means you take the only the polarity, only the magnitude. Don't consider polarity of negative positive. You must ignore that. Okay. And you must remember 80 volt RMS. 80 volt RMS means the RMS value is 80 volt. Suppose they have given instead of this 80 volt, suppose they are given instead of this 80 volt source, they can write like this. Okay. They could write it like this. You could write a voltage source of 250 volt. Okay. This will be the peak value of the sine wave. If this is the peak value of the sine wave, what is the RMS value of this voltage source then?
Divided by root 2, sir.
Divided by
2, root 2.
okay, divided by root 2. Okay, so that
Hello, sir.
yeah, tell me.
Sir, divided by root 2, sir. IRMS equal to I naught divided by root 2, sir. VRMS equal to V naught divided by.
Yeah. Okay, so 250 divided by root 2. So yeah, so they could confuse you. They could instead of this, they could just write it as 250 into sine of omega t plus 30 degree, something like this. They can write. But effectively, what you want to know, you want just the RMS value. So the RMS value is 250 divided by root 2. Okay. So that is what I
Okay,
think
sir. Okay, sir.
consider. All right. Then one more thing is the I told how to see the polarity. This polarity thing is a very confusing thing, and the only way you can get mastery over it is by practicing. By repeatedly practicing, you will be able to what you say eliminate your silly mistakes, your silly errors which you make. That's the way to go about it, and you have to apply KVL, KCL everywhere. So we did over here, we applied KVL over here. So what we did, we this positive, then we consider drop across this. Let me go to that one actually. We consider the drop across this self-inductance and a drop across this. That is the actual KVL. That is the actual what you say. This is the loop which we have considered. So those such things also you must be able to do it without making any mistake. Right? Any doubt in that?
No, sir. No, sir.
Yeah.
Sir, your teaching is very, very amazing.
Oh really? That's thank you. Thank you.
Yes, sir. Yes.
Yes. Only thing is you must get good marks. And solve fast.
Do you know Tamil, sir?
I can understand, I can't speak.
Okay, sir.
Yeah. So that's there. Then yeah, how to determine the polarity by seeing the direction in which the current flows. In this coil, what is the polarity of the voltage induced due to current flowing in this coil depends only on the direction of the current flowing in this coil, not on the direction of current flowing. Let me again tell slowly. The polarity of the voltage induced in this coil depends only on the direction of current flowing through this coil. Okay. And at the dot we put plus, at the other side we put minus, and M2 into d of dt into the current flowing into the coil. Okay, so the current is flowing out of the coil, we just multiply it by -1. Right? Yeah. Then we found out these equations in terms of di1, di2, all that. But in case it was, we just in our problem set, in our assignment which we solved, we just replace d by dt by j omega. Okay, we just replace it by j omega because we are just worried about the steady state. Okay, and in the questions they just directly gave us the value j16, j36. We didn't even have to multiply it by omega. Okay, the values were just given. Right? Okay. Yeah. So any other doubts you have?
No, sir. No, sir.
No doubts. So currently you're doing which week?
Sir, week 6, sir.
You're solving week 6 assignment right now.
Yes, sir. Due date Wednesday, sir. Coming Wednesday.
Yeah, it's the one.
The Laplace transform, sir. Very easy only, sir. Laplace transform.
Oh, it's very easy.
For me, easy, sir.
Yeah. It simplifies, it makes it easy actually.
I already studied in mathematics, sir. Laplace transform.
Already studied that?
Laplace signal and system.
Okay. Oh. Then it is simple actually. Laplace transform is good actually. Yeah. Then no other doubts? Yeah. If you don't have any doubts, we can end the meeting. Yeah. Thank you then. Bye.